So it's my pleasure to introduce Nicanor Carrasco-Vargas from Jagiellonian University, who will talk about strong topological Rokhlin property and Medvedev degrees of SFTs.
Hi. I wish to thank the organizers for this very nice month and also for the opportunity to speak here. So, as the title says, I will talk about the strong topological Rokhlin property and Medvedev degrees of subshifts of finite type. So, please interrupt me all you want. Then, in this talk, all systems are topological systems. So, by that I mean continuous action of a group on a compact metrizable topological space by homomorphisms. And here, two actions are the same if they are conjugate, meaning that there is a homomorphism of the spaces that intertwines the actions. Intertwines means. Then, a countable group has the strong topological Rokhlin property when in the topological space of all continuous actions of the group on the Cantor space, there is a residual conjugacy class. So here we're looking at all actions, not necessarily transitive actions or free actions or faithful actions. So for instance, the trivial action on a single point is also here, all actions. Here, the space of actions has the uniform topology. So well, here I cannot use the empty notation for actions. So sequence of actions converges to one action if for every group element and x converges to x uniformly on the Cantor space. And the conjugacy class of an action is the set of actions conjugate to it. So, well, this property essentially says that in the space of actions, there is one action whose conjugacy class is very big. Then you can ask which groups have this property. So the first example is the group of integers, and this is now famous theorem of Jekris and Rosendahl. But after we know that the integers have this property, it's natural to ask which other groups have the same property. So for instance, finitely generated free groups also have this property. Free products of finite or cyclic groups have this property. Set to the D for D at least 2 does not have this property. And more generally, finitely generated virtually nilpotent groups that are not virtually cyclic. And also, many other groups don't have this property that I will not mention. And but I will exhibit some new examples of groups not having this property. This is the content of the preprint in which this talk is based. So for instance, bonds like solitary groups, Laplater groups, some branch groups, and products of two infinite recursively presented groups. So, well, this contains some of the previous ones. So, Michael Duha proved that this strong topological Rokhlin property can be characterized in terms of the space of subshifts of the group that we are considering. And this is the characterization. So a finitely generated group has the strong topological Rokhlin property, so there is a generic action. If and only if projectively isolated subshifts are dense in this space of subshifts. So we fix an alphabet A, and we look at all subshifts contained in A to the G, and this is a set. We can give it a topology in the next slide. So the statement says that a specific class of subshifts that will be defined later is dense in this space of subshifts for every alphabet, for every finite alphabet with cardinality at least. So here A to the G is the set of functions from a finite alphabet, and it's given the discrete topology to shift action by translations. This is the usual shift actions for groups. And the subshift is a closed shift invariant subset of this. Then, and a subshift of finite type is one which we can define by forbidding finitely many patterns. And after you choose your favorite metric for A to the G, well, it's meterizable, then that metric defines a Hausdorff metric for all the compact subsets of your initial space. And then one can use this metric for the space of subshifts, because subshifts are compact, because, well, A to the G is compact, so its closed subsets are also compact. And this collection of subshifts with this topology is homomorphic to a closed set of the Cantor space, so it's zero-dimensional, but it's not necessarily a Cantor set itself. It always has isolated points. For instance, any finite subshift is isolated in this space of subshifts with this topology. Also other things, for instance, minimal SFTs are isolated, and possibly more things. Now here is the definition. So
when you say finite, you mean finite type? What is finite?
Finite as a set.
What does it mean, finite?
So when I say that this one is finite,
Oh, just finite.
I mean,
it's finite.
But it's finite. So finitely many configurations. But well, there are also infinite ones, more interesting ones that are also isolated ones. So let me write something else. So, well, here is a definition. So the definition says that a subshift on alphabet A is projectively isolated if there is an alphabet B and a continuous shift equivalent map from B to the G to A to the G. This one that does something, but I want to observe that if I go to this full shift to this full shift, then it is a function. Maybe we can call it with a different letter. From the subshifts of B to the G to the subshifts of A to the G. So we send a subshift to its image by the function. There are some notational ambiguities that maybe appear, but it is just so. If we assume that this function is continuous and shift equivalent, then the image of a subshift is also a subshift because, well, it's closed because the continuous image of a compact set is compact, and it's also equivalent because the map is equivalent. So, well, then we have a new function from the other space of subshifts. So this definition says X is projectively isolated if there is some continuous shift equivalent map such that when we look at the space of subshifts in alphabet B, like the new one, then there is a whole open set which collapses to the singleton X in its own space of subshifts, right? So, well, maybe that explains the terminology. Then this is a theorem which I like a lot, which says that projectively says that isolated points are dense in the space of subshifts in any alphabet for the group of integers. So I think this is very strange. So here is a picture representing that the space has many holes, so each hole has a singleton, which could be an isolated point. But these isolated points are dense. So this is actually a Pechinski space, which is a zero-dimensional topological space with a dense collection of isolated points. And the complement of the isolated ones is a Cantor set. So that characterizes, well, all spaces with these properties are Pechinski spaces, and they are all homomorphic. So yes, well, then if we put these two theorems together, the first one says that isolated points are dense, and the other says that the strong topological Rokhlin property characterized by the density of projectively isolated subshifts. So if we observe that isolated ones are in particular projectively isolated ones, we recover Kekuri's and Rosenthal's theorem that the integers have the strong topological Rokhlin property. Maybe an observation when isolated subshifts are projectively isolated. So if this is an isolated point, then there is a neighborhood. Well, the singleton containing this subshift is a neighborhood. That's a definition of isolated point in a topological space, that the singleton of that point is open. So then the identity map from this space to itself with this neighborhood realizes the definition of projectively isolated, because the identity map sends everything in this neighborhood, which is a singleton, to X. So isolated points are in particular projectively isolated. And maybe isolated points, well, for the integers, we get something much better, which is that isolated points are dense, because not all projectively isolated subshifts are isolated. It's not the same. But
do you have a good example of that?
Yes, so isolated points must be SFTs. One can observe that from the topology of the space. But there are suffix subshifts that are not SFTs that are projectively isolated. So the easy example is the semi-side up. So for instance, in the integers, if we look at the subshifts in 1, configurations, have at most one. This one is suffix. Called sometimes, let me say that. So this one is suffix. It's not SFT, but it's projectively isolated. It is an open question if the density of isolated points is equivalent to the density of projectively isolated ones. But well, this is what it's known for now.
Known for?
Sorry?
It's known for in some case? Or?
It's just not known. Known that projectively isolated points are different from the isolated ones. But well, I think it's not known. So for instance, for the integers, the two things happens. For finitely generated free groups, projectively isolated subshifts are dense, and I don't know if it is known if isolated ones are dense or not. Well, we have this. Then, using Duha's theorem, we can state an apparently simple criterion for the failure of the strong topological Rokhlin property. So here is the criterion. Take a finitely generated group, And we take a partially ordered set, which suggestively I denoted by R with a minimal element, and a function H from this space of subshifts to this partially ordered set. And we assume that the following things happen. So maybe you can initially think of entropy, but entropy will not work because of the first property. So we need that this function H gets bigger when we pass from a subshift to a smaller subshift, to a subset. So this says that if X is a subset of Y, then H of X is bigger than H of Y. Well, this makes sense because it's a partially ordered set. So we can say this. And we also need that for every projectively isolated subshift, this function attains a minimal value. And we also need that some SFT has non-zero value by this function H. If this happens, then the group does not have the strong topological problem. And
excuse me, may I ask about the previous slide? Let's say you take the result of Hoffman. What is known about Pavlov and the Schmidling when you replace Z by Z, K bigger or equal than 2?
It is known that projectively, it is known that isolated subshifts are also not dense. That actually that will also follow from something in the next slides. But that is a first observation, and it's known that but it's known much more. So you have the space, and then you have the isolated points, and then, well, it's known they are not dense, but then you can remove the isolated points and see what you get. And there is this notion of Cantor-Bendixson rank, which tells you what happens when you iterate that process. And it's known that it has infinite Cantor-Bendixson. Maybe you can mention it. It's a theorem of Nunez. So, well, that is maybe what we know in precise terms about.
Infinite means omega,
I
or you just know it's infinite.
am sincerely not sure, but it's clearly stated in their paper.
Yeah.
I'm sorry, I'm not sure. So I
It
prefer
could be any cardinal. Ordinal.
right. No, I'm sorry. I prefer not to lay or to.
One more question about the slide that you just had. So in Duha's theorem, you consider alphabets with cardinality greater than 2. So what about cardinality 2? So just 0, 1 alphabet?
You ask if it is sufficient to look at that alphabet?
So the theorem says that it has to be dense in all shifts with alphabet greater than 2.
Sorry, no, this is a typo. It should be at least.
Okay.
I'm very sorry.
Special about 0.
There's nothing special. The special one is alphabet 1, but then everything is yeah. I'm sorry about that. Okay, so here is the criterion. The proof is actually very easy. It's just a corollary of Duha's theorem. So here is a proof by picture. So the assumption is that we have an alphabet A and a subshift X, this one here in red, such that H of X is non-zero. So, well, this represents the partially ordered set where H takes values and H of X is non-zero. Then, importantly, because X is an SFT, the collection of shifts contained in X is open. That is not true for all subshifts, but it's true for SFTs. It's actually a characterization of SFTs that is proved in the paper of Pavlov and Schmidi, the same one, and it's proved for the integers, but the same proof works for all groups. So, well, the collection of subshifts of X is open. So here is the neighborhood. Then, well, we also know that projectively isolated subshifts have zero H. That was also one of the assumptions. And remember that to disprove the strong topological Rokhlin property, it is sufficient to find a neighborhood, an open neighborhood, without projectively isolated subshifts. The characterization said projectively isolated subshifts are dense. So we only need to show they are not dense. So I claim that this open set containing X is an open set containing no projectively isolated subshifts. Why? So if there was some projectively isolated subshift inside this neighborhood, then remember that this property gets bigger by inclusions. So this was one of the assumptions. This is the Math-Frac page. So anything inside this neighborhood will have at least as much H as X, because it gets bigger for inclusions. So everything here has non-zero H in particular. So then there cannot be a projectively isolated subshift inside, because we assume that they all have zero H. Make sense? It's very simple. It's just a consequence of the assumptions and the fact that SFTs define the topological fact that the subsystems of an SFT are an open set in this topology. Okay, so here's a proof. So then, well, this is not a question, but whatever. So to actually apply the criterion, we need to find a function H with these properties. And I have said this a lot of times, but we need that H, whatever it is, gets larger when we go to subsystems. So things like entropy will not work. Then, so well, I will talk about Medvedev degrees because they are something that has the properties we need. So here is a picture representing the fact that Medvedev degrees are very good. So, well, then I will give a loosely precise definition, but well, Math-Frac M is the lattice of Medvedev degrees. They are not real numbers, they are something which lives in a lattice. M of X is the Medvedev degree of X, and well, they have the properties we want. So they get bigger when we go to a subset. And we will see that the Medvedev degree of a projectively isolated subshift is 0. So then we only need SFTs with non-zero Medvedev degree to apply the criterion. So what are Medvedev degrees? So this is a notion from computability theory or recursion theory. So I will not define computable functions, but they are something. So given two subsets of the Cantor space, not necessarily subshifts or shift invariant, just sets. Given two sets P and Q, we say that P has more Medvedev degree than Q. If there is a computable function from P to Q. So then,
is it supposed to be surjective or injective or any?
Nothing. It's a computable function on the Cantor space, so its domain is, I mean, it's a partial function, so its domain is just a subset. We don't ask something about its domain, but this implicitly means that its domain contains P, so it's defined for every element in P, and the image of anything in P is in Q.
That would be just one point, the image.
Is 1 point, like P or Q?
Right. I mean, the image of P in Q potentially could be just one point.
It could be potentially just 1 point. So for instance,
Q is contain a computable number, then
if Q contains a computable number, you can define, I mean, if Q contains a computable sequence, denoted by XC, then for every P, you can define the function which sends anything to this point, and that shows that a set containing a computable point is minimal for this relation. So, and so we say that so P and Q have the same Medvedev degrees. Each one is at least has at least as much as the other. So well, this is a relation, but then we can define this. I think it's called the symmetric version. Okay, so they have the same degree. We have both reductions. And then this math frac M is the set of equivalence classes by the induced group, which is this one. So, well, this is maybe looks like abstract nonsense because they have also not defined computable functions, but the underlying philosophy is that the underlying philosophy when someone defined this is that one identifies a mathematical problem with a set of solutions. So every element in the Cantor set, one regards it as a solution of some problem. And the Medvedev degree of a problem is measures how hard it is to find some solution of the problem, any solution. So if the problem has a computable solution, meaning there is a computable element in the set of solutions, then it's easy in this like complexity measure. So this is a complexity measure. And importantly, if P is a subset of Q, then finding elements in Q is easier just because it's a bigger set. So we are looking at a problem with more solutions. So that is why Medvedev degrees get bigger when we pass to subsets, which is what we wanted. Maybe funny observation is that in this relation, or maybe in this lattice of Medvedev degrees, there is a maximal element. And the maximal element is the Medvedev degree of the empty set. Why? Because in this relation, the hardest problem is one with an empty set of solutions. Well, that makes sense. So a problem is very hard if it has no solution. So here this corresponds to maximally hard. Well, the actual proof with the definition is that the empty function goes from the empty set from the empty set to whatever. Right? But that's nonsense. Well, I like this part. I find it fun. So then if G is a finitely generated group, then there is a natural way to computably identify A to the G with a subset of the Cantor space. And then we can define Medvedev degrees of subshifts. Now this looks like obvious because we all know that A to the G is a Cantor set, but that does not mean it's computably homomorphic to a Cantor set. So it will not be, we cannot in a meaningful way computably identified with the whole set. It will be a proper set, which topologically is also a Cantor set, but it's not computably homomorphic to octets. But then the nice thing about subshifts is that we have the Curtis-Hedlund-Lindon theorem, which says that all continuous and shift equivalent maps are defined by a sliding block code associated to a finite window. And so those maps are computable, like automatically. All morphisms or subshifts, all morphisms of subshifts are automatically computable. So then Medvedev degrees are interact very well with dynamical notions because morphisms are computable and computable functions are the thing in the definition. So first, they are invariant for topological conjugacy. Also, if X factors onto Y, that the map that realizes the factor is automatically computable. So then X has more Medvedev degree than Y. If X embeds into Y, also it has more Medvedev degree than Y. And if X is a subset of Y, then also it has more Medvedev degree than Y because the inclusion function is computable because of that. So
you said that a factor map is automatically computable.
But by the Curtis-Hedlund-Lindon theorem, so it's it implies that there is a. Do you want me to state it? So maybe
But just to clarify, you did not define computability, right?
I'm not defining computable functions.
So,
but maybe it makes sense
discussion
because it's
for those who
fine.
don't know what computability is a little bit.
It's weird, but I think it's intuitively. I mean, I believe that it should intuitively make sense that maps defined by a finite window are computable because there is something finite in them, and generally, I know when we have.
Basically, computable means that you can write a program on the computer which will write your map.
Oh. You hope.
That's what it says. Well, it means that it will read as many digits as it wants to produce a given digit in the image.
Not necessarily. It's a stopping.
I mean, each digit you can compute in finite time, but since there are infinitely many digits,
Okay.
what they cannot produce.
Here is a picture of the Curtis-Hedlund-Lindon theorem. So it says that continuous shift equivariant maps between subshifts are determined by local functions. So what this means, here is a configuration X, here is its image, phi of X. So the theorem says if we want to know what color to put here, well, if we think that the alphabet is a set of colors, then we only need to look at the pre-image configuration in the same place. So here is X, and then we look at a finite set, which I think is F or maybe the inverse. Well, this finite set, so this is a finite subset of the group, and we look at what colors are here, and the local function, which is this one, tell us what color to put here depending on this one. So it's like a word to symbol function, but instead of words, we have finite patterns in the group. I'm not sure if this looks intuitively computable, but hopefully. So, well, now here is the main result, almost. So it says that a projectively isolated subshift on a recursively presented group has 0 Medvedev degree. So now if we remember the picture, we wanted this property, this occurs always, by definition of Medvedev degree. This condition is what we have in this statement. So to disprove then the strong topological Rokhlin property, we only need an SFT with non-zero Medvedev degree. So then, as a consequence of the previous result, we have the following criterion. So if a recursively represented group has an SFT with non-zero Medvedev degree, then it does not have the strong topological Rokhlin property. But it's a consequence of the previous result and the criterion, which is like a general thing. And I say non-empty because people allow the empty set to be a subshift, or some people don't, and generally it doesn't matter. But since the empty set has maximal Medvedev degree, that's was in the picture you raised. If we allowed the empty set to be an SFT, then this is always true because it always has very big Medvedev degree maximum. So that's important here. Now, constructing such SFTs is not easy, but it has been done for many groups. So for instance, for set to the D, this is known it is known how to do this since a long time ago. This was done by Hanf and Myers. So for this one, we recover Ochman's result that set to the D does not have the strong topological Rokhlin property. It is also known for instance, bounds like solitary groups, for Lamplighter group, for products of two infinite groups. It should say products of two infinite recursively represented groups, and also for more groups. So something nice about this is that after we have some groups admitting SFTs with non-zero Medvedev degree, then we can obtain more groups with the same property. So here is a proposition. It says that among finitely generated groups, this property, admitting an SFT with non-zero Medvedev degree, satisfies the following. So first, it's transferred to supergroups. So if you have a group, and then you pass to a bigger group in the sense of a group inclusion, then the bigger group will also have the property. It's transferred to group extensions. So if your group factors onto a group with the property, then the big one also has the property. And it is an invariant of commensurability. It means that two groups share a finite index subgroup. And it's also a quasi-symmetry invariant if the groups are finitely represented. So, well, after we have some groups with the property, we can make more groups. And this is one reason that this is nice is that some possible analogous statement of this for the strong topological Rokhlin property of a group or its negation is not known. So from what I know, it's open if it's a quasi-symmetry invariant, even for finitely represented groups. But for this property that implies a strong topological Rokhlin property, we have such thing. So that's a good thing. Now I will mention some ideas of the proof. So I need some notation. Maybe it's better if I write it here. So if X is a subshift, the language is the set of finite patterns that appear. Then the co-language is this set of patterns that don't appear but in the same absolutes. And it's also convenient to restrict these things to finite sets. So if F is a finite set of G, Then we have the language and co-language, which supports some finite set of it. And we use these things, so better to define them. So then a general thing that happens is that a subshift with decidable language has zero Medvedev degree. So having decidable language is a stronger property. It's in general stronger, or in general maybe much stronger, because if you have a subshift and you add a computable point, like maybe a singleton, a fixed point, then the Medvedev degree trivializes always. But that does not mean that the language of the new subshift is decidable or something. So here, decidable means that there is a computer program or a Turing machine which will input a pattern in this case, runs for some time and eventually tells you if the pattern is or not in the language, which is this. So what we will actually prove is that a projectively isolated subshift on a recursively represented group has decidable language, which is better than proving that it has zero Medvedev degree. And I should say that this improves a previous result of me and Matías Savellit and Alonso Núñez. So we proved the same thing, but for isolated points and for groups with decidable word problem. So this is better because isolated points are in particular projectively isolated, but not the other way around. Well, the proof is also different. So the first half of the proof is for free in the following sense. So let's fix a recursively presented group, G, and a projectively isolated subshift. And then we observe the following. So first, the projectively isolated subshift is something. This is something I mentioned. And this follows from the definition of projectively isolated, but I'm not sure if I said it right. So the reason is that so if X is projectively isolated, then there is an open set in the space of subshifts on some different alphabet, which is collapsed to this projectively isolated subshift. But SFTs are dense in the space of subshifts with this topology. So we can always pick an SFT here. And then the image of this SFT by this continuous shift equivariant function will be X. So then it follows that it's a factor of an SFT. Okay, so, well, or whatever projectively isolated subshift must be Sophic. Then it is a general property that co-language of a Sophic subshift on a recursively presented group is always recursively enumerable. So that means that there is some algorithm which we give it a pattern which we want to know if it's in the language or not, and the algorithm runs and stops if and only if the pattern does not appear in the subshift, if and only if it is in the complement of the language. So that is one half of the decidability of the language. So this means that there is an algorithm which can input a pattern, stops if and only if it's not in the language. So then to prove that the language is decidable, we only need to prove that the language is recursively enumerable. This means that there is another algorithm which, given a pattern, stops if and only if it is inside the language, like the opposite thing. Well, this is an equivalent condition of decidability, because if we have both algorithms, then we can, if we want to know if a pattern is in the language or not, we run both algorithms, like in two computers, we can do that. And eventually some of the computers will stop and tell us if it is inside the language or if it's outside the language. Okay. Now, the other half of the proof is the interesting one, and which uses that the condition of being projectively isolated. So here is another picture. So we start with the claim is that there is an algorithm which can input a pattern, else if and only if the pattern is inside the language. So we fix a pattern, P, input. Let's take P. And now we do the following things. So for projectively isolated subshift X lives in some space of subshifts with some alphabet, right? So then we define XP. Can you see the letters, or is it too small? So we define something depending on the pattern. So it's a subshift of configurations where P does not appear. So we want to know if P is in the language of X. But then this happens exactly when XP is a proper subset of X. Because if it's not in the language, then we removed nothing and XP is equal to X. Okay, so now in the space of subshifts, we have two things, X and XP, and we want to know if they are equal. Now, we remember that X is projectively isolated, so there is some other space of subshifts. And there is an open set in this space, and there is a continuous shift equivalent map that collapses this open set to our singleton X. And for topological reasons, we can assume that this open set is a neighborhood of an SFT. So we can pick an SFT, Y, and we can assume that this open set is exactly the set of subshifts whose language of support E, for some E, is equal to the language with support E of Y. So these are the subshifts whose language coincides with the language of Y in the support E for fixed E. Okay, we have an open set. And now we define a subshift, which again depends on P, which is YP. So YP is essentially the pre-image of XP. YP are the element Y, which is an SFT, and which we already fixed, whose image is the XP. Now we want to know where is this guy, because if it is inside this neighborhood, this case, then by definition of projectively isolated, it will go to X by the map phi. But we also know that the image of YP is XP. So then that implies that X is equal to XP, and then that the pattern is not in the language. If it is outside, then it must happen that XP is different from X, because if they were equal, then YP would be equal to Y, right? Because it's defined as the pre-image of XP. So P is in the language, we finally XP is different from X, but then this is equivalent to the condition that YP is not this set E. But okay, so we want to know if it's inside or outside. By definition, YP is a subset of Y. And it will be inside if and only if its language with support E is equal to the language with support E of Y. So it will be outside if and only if the language with support E of YP is properly contained in the language with support E of Y. And the thing is that this one is a recursively enumerable condition. So it's also equivalent to the assertion here that the complement of the language of YP intersects the language of support E of Y. It's just a rewriting. So the boring part of the proof is that the pre-image of XP, which is YP, has a recursively enumerable colanguage. So we can recursively enumerate things that are not here. And we will know that it is a proper subset if and only if something in the language of Y with support E is enumerated, because then we know that the language of YP with support E is a proper subset. Well, that's all the proof. And thank you.
General question, what will be the next step in this direction research? Open questions.
So one open question which I like and which I think should be tractable is whether the strong topological Rokhlin property can be transferred between groups in the same way as this property. I think it's good. Well, yes. Maybe that.
Can you make sense of the question? What is the generic case as this property or not? So, to some collection of.
I believe that most groups don't have the property. I think the only known examples among finitely generated groups are free groups and maybe virtually free groups. I think there is not a conjecture about which groups have the strong topological Rokhlin property, but I believe that in some sense most groups don't have the property.
Kind of interesting connection. I mean, you can try to ask a similar question for other groups than the Cantor homomorphism. Like take a different Polish group and ask which is which groups have the property that an embedding, a generic embedding has, and we have a very similar proof to this Ducha theorem. It's a theorem of mine with Kitrosser and Julien Melleray on the Polish symmetric group. Namely, a group has a generic embedding into S infinity if and only if the isolated subgroups are dense with the Chaboty space.
Okay, so it's very analogous. But
so it's kind of a connection to the previous talk in a way. Similar statement also.
Right, but with subgroups instead of subshifts.
Subgroups instead of shifts.
So, well, thank you.
Any other questions or remarks? Well, thank you, Carl, again. The 5 months semester, we resume our week on We're gonna learn instructions tomorrow at 9:15. As usual. After
But I didn't know.
what do we have?
Oh, yeah, you. Many times. It's hard to keep track.